Hi, everybody. Thanks for joining the deck.gl workshop. My name is Xiaoji. I'm an engineer on Uber's visualization team. My day-to-day job involves building high-performance, heavy-duty visualization applications in the browser, as well as the framework level libraries that support them. In this workshop, I will take you through some simple examples to get started visualizing some geospatial data in the browser with deck.gl. Who is this workshop for? I can think of a few roles that would be interested in this. Developers that build web applications, obviously data scientists who need to deal with large amounts of data and just need to quickly check the shape of their data with a convenient tool. Designers that work with the visualizations. I myself used to be a designer, and I know it's really difficult to fake or mock up a visualization that involves a lot of data. And we deal with people who we call open data hackers or hobbyists who are very enthusiastic about open data that's released, for example, by companies and governments, and they want to extract insights into this data in their spare time just for fun. What you need for this workshop, you can get access to these slides through t.uber.com/deckgl tutorial 2018. That's probably the easiest way because we have some very sophisticated URL after this. We will use observable just like Nick's H3 workshop did. So you can skip all the local Node.js and NPM setups. It's not required that you have prior experience doing visualization or graphics in the browser. It'll be nice if you can read and write a little bit of JavaScript. So what is deck.gl? deck.gl is Uber's open source WebGL-powered framework for large-scale data visualization. It started internally because at Uber, we deal with billions and trillions of data points that's collected from trips about urban mobility, about people's movement, and about traffic conditions every day. And we needed tools internally for data scientists, operators, and engineers to monitor the performance of the marketplace and our data models and our interaction with our users. And those things are not very easily done in the browser without with the tools that we had at hand. So we built some of our solutions from scratch in-house. So how does geospatial visualization work? Consider you have a location that is a longitude and latitude. What happens is if we're using regular mapping solution like Mapbox or Google Maps, you will need to project that to the web marketer plane, which is not a linear transformation. There are a lot of logarithmic and trigonometric operations involved. So it's fairly expensive when you have tens of thousands or hundreds of thousand points. And then you position a camera that look at the web marketer plane, and that camera can be put into looking at one area, one city, and you can rotate around it inside the browser to provide a better view of your data. So when we're doing this for one data point, it's fairly easy. If you are dealing with say 3,000 points, it's kind of doable with CPU and DOM-based visualization libraries such as D3.js. But anywhere beyond that, your browser just chokes. Because when it adds up, it is actually a fairly expensive operation to go from the bits to the pixels. Luckily for us, WebGL provides us with a really nice solution for this. While GPU can have like smaller processing capacity comparing to the CPU, what it can do is to do a large amount of the same operation in batches. So if you think of this visualization process as a mathematical transformation from the geolocation coordinates to the on-screen pixel coordinates, then dealing with millions of points in the browser is basically repeating that thing over and over again, and GPU is precisely designed for that. And in deck.gl, we provide shader modules that implement common visualization transformations such as Mercator projection. So in this example, we have almost 1 million points rendered as scatter plot showing the population density in New York City. And all the points are just uploaded to the GPU in this raw form in longitude, latitude, and altitude. And the GPU is handling all the heavy lifting of figuring out where exactly they should be rendered on screen. And all that the CPU does after that is just to deal with the user mouse interaction and figure out where we should position the camera next, which is fairly cheap. This is another example using GPU to do filtering. Here we're showing the county-to-county migration in the United States. That's between 3,200 something counties to every other county in the country. And if we just show all the connections on one map, then it's plainly unreadable. So the interaction we provide here is we will filter out only the links that is going in and out from the region that's under your cursor. And what's happening is the GPU actually receives all the raw data of county-to-county connections, and the CPU just sent the XY position of the mouse to the GPU, and GPU is doing all the heavy lifting of figuring out which arcs should be rendered in what color. So in deck.gl 6.2, we introduced some really nice features such as GPU transition. It's probably a little hard to see in this screencast, but as we are dragging the year slider there, it's actually transitioning the color from one dataset to another. And this is done on over 100,000 line segments. And it's all, the interpolation is all done on the GPU. And we also use GPU to do aggregation. This one is aggregating 4.5 million pickup drop-off locations in the New York City. And as we pan around the viewport, every time the camera moves, we are re-aggregating the counts of points inside each screen grid. And this can be done very efficiently on the GPU at 60 frames per second. So with that said, I encourage you to click on this link, and again, the link to the slides is on the bottom. Click on this link, and we can try out deck.gl for ourselves. So if you click on the link, you should be able to fork it and edit it as your own. What we're looking at here is basically a boilerplate template for you to get started using deck.gl. In the beginning, we import several libraries that will be needing in the follow-up coding. First, of course, we will import deck.gl. So basically, this line requires the library and the object up here. If you expand it, it shows you all the public APIs that is exposed by the deck.gl library. And the second thing we import here is Mapbox.gl. Deck.gl is designed to work seamlessly with Mapbox.gl as a base map provider. deck.gl itself doesn't provide any map information, but we designed it in a way that the description of our camera, basically longitude, latitude, zoom, pitch, and bearing, when you provide the same settings to both Mapbox and deck, they produce identical projection matrices, so that the rendering results will be synced. Lastly, we are importing D3. This is just a really nice utility library for visualization. We'll be needing this for loading data, parsing data, and doing some color processing. In the sample data section, I already added here that loads from a pre-existing static file that describe all the road accidents that happened in the UK between 1979 and 2016. If you expand this array, basically each item in the array has a longitude and a latitude that describe where that accident happened. So this will be the sample data that we start working with. Now, the first thing you want to do is you want to create a new deck.gl instance. Here we're saying we want the container to be this HTML div object. So that's where we'll draw the map, and we will use Mapbox as the base map provider. And it needs a API token to be able to use the service. And then this part, we describe the initial view state of the map. This is what you will see when you first load the page. And then right now we're rendering no layers, and we will be adding some deck.gl layers pretty soon. So this is what you get by running that. You can zoom and pan and do all sorts of stuff. So because we're dealing with UK, I'm just gonna change this to something more manageable. All right, maybe not that close. All right, good enough. Now let's go add some layers. So the way you create layers is you just call the constructor of a layer. Here we are doing deck.gl's scatter plot layer. We want to pass the UK road accidents variable to it as data. And let's just go see the documentation of what it has. So for each scatter plot layer, you need a data array. And then we have things that we call accessors that will let you specify how to extract information out of that each data item. So you need to tell deck.gl what to use as the position, radius, and color for each point. In our case, this is the shape of our data, longitude, latitude. So we want to do, for each item, we will return an array that's in the shape of longitude, latitude. You can supply a third component that is the altitude if needed. And then for simplicity, I will just say all the radius is 1,000 meters. And all the colors are orange. Oh, need to return it. Now what I need to do is when I render the deck.gl canvas, I will pass the layer I just created to the layers prop. Now you have nicely positioned points all over UK that shows you where the accident happened. Okay, in reality, we have like much denser points in here. So let's make this 50 meters. Now you can notice that we can see it much better zooming in, but when we zoom out, they disappear because 50 meters is not really visible from space. We have some solution for that. That is have something called radius min pixels. That means when you zoom way out, this is the minimum number of pixels that we will use to render each point to make sure that they don't fall off the map. Now, no matter how far you go, like there's a minimum size that will render each circle. But when you go in, obviously they're still rendered at 50 meters radius if needed. No, it is rendering everything. So that data set is 140,000 points. That is very manageable for deck.gl. We can deal up to, I want to say 2 million is easy in a decent laptop and browser. If you want to go like 10 million or 30 million, it's probably getting a little frame rate choke, but still kind of usable. So why do you have the question that if this is sampling? Because a lot of the circles are overlapping each other. Like they are rendered with a very small translucency, and you can see that there's a pile of circles here, but you can't really tell exactly how dense that is. This is because scatter plot is not the best visualization type when you are dealing with like distributed data like this. We can go shop for another layer that can potentially solve that problem for us. We have a bunch of aggregation layers in the deck.gl core layer catalog that will automatically show you the aggregated results. Let's go try a screen grid layer. So what it does is it divides your screen into a grid of fixed pixel size. And as you are zooming or panning around, it updates, it counts how many points falls into that little cell on your screen. So you can see how many there are in there. So let's go do that. I'll change scatter plot to screen grid layer. We still need get position. Get position. I need cell size pixels. I'll make it 5. So now you can really see how dense the accidents are around the London area. As you zoom in, it will show you a little more detail, and you can sort of see the texture of the streets there. But most importantly, it gives you an almost a heat map of how these things are distributed around geospatially. If you want to go fancy, we have a nicer aggregation layer called the hexagon layer. It works very similarly. It has data, get position, and has radius. So let me make radius to be 10,000 meters. And we can make it 3D by saying extruded is true. Oh, I should probably set the elevation. This is just a multiplier of the extrusion. Now this is rendered in full 3D, so if you rotate around, you have this lighting effects, and you can see how things line up. I'll make radius just 1,000. So you start to see much nicer fine grain aggregated accidents distribution that are basically concentrated around urban areas. One thing that we found really useful in our internal applications is when you have a distribution like this, basically the downtown London is taking all the attention away from the rest of the country, and you can't really see how the rest compare. So you can do something called upper percentile to filter out, say, the top 2% of your data. Now that downtown London is removed, you can really see how the rest compare to each other. You can consult the documentation of each layer to see how you can customize them. For example, the color scale of each layer and how the elevation is handled once the aggregation is done are all customizable. Okay, now we've done playing with that data set. Let's go back to San Francisco. In this example, we are going to get some more real data. So I'm going to SF data. Sorry, datasf.org. This is a website where you can find all the open data from the city of San Francisco. And let's look for building heights. Historic height and bulk districts. So basically, it'll give you the footprint of blocks and will tell you the height of buildings on that block. And what we could do is say export, and we want GeoJSON. I'll just copy that link address and go back to our notebook. And tell D3 to load that URL. Okay, now that's loaded as a GeoJSON. We can see the shape of data here. Each polygon has a field called gen height that is that's the number that maps to the height of that building. So we can go use the GeoJSON layer of deck. To visualize that data. All right, that's just the default color. So I'll say get field color. So we'll return an RGB value here. I would like the color to code the height of that building for me. I'll say, I'll take the height property, make it a number. So when it's more red, it is higher. Okay, so now that doesn't look right to me, right? That's the Golden Gate Park. That shouldn't be tall. What I can do is, let me just add a little object there that will show me some additional info. Now, on my layer, I want to say, I want to make this layer pickable. That is, I will make it interactive. And on user click, I want to change the content of that info label to the height of my block. So if I go click on some random place that is 45, sure. Okay, so Golden Gate Park's height is 99.99. That's obviously not right. Let me go fix that and say, if height is more than 5,000, we'll just make the alpha to be 0, so we won't be able to see it. Okay, now that heat map looks a lot better. The GeoJSON layer will also allow you to extrude polygons. So I'll tell it to be extruded to be true, and I want it to be extruded the amount of the height. I think we still have some very tall buildings around the area. Now you can see how things nicely lined up around Market Street. I can probably use D3 to create some better color scales. So I wanted to go from green to yellow. To red. Oh, here. If it's a reasonable height, we want to call scale on the height. Otherwise, just don't do it. Oh, I broke it. Was not happy now. All right, I don't remember how to use D3. Never mind. Huh? I think it might be that. Oh, yes, you're right. Nope. That needs to be an array also. Yay. Huh, I still have something really weird going on. Oh, let me move my filter. To just make them high 0. That's better. So a lot of these things you can do with Kepler-GL if you are not comfortable with coding. But with deck.gl, apparently there's a lot of flexibility on what you can do to filter and manipulate your data, and how do you define the scales, and how you want to define the user interaction in our case. So at the visualization team, over the last about 3 years, we've built a full visualization stack for the web from bottom up. We have React wrappers for React Viz, and for D3 that is called React Viz, and for Mapbox.gl that is called React Map.gl, that works with our deck.gl library. Deck.gl used to be React specific. It no longer is, so it can now be used with what we call pure.js or vanilla.js. You can use it with whatever UI frameworks that you prefer to do. And that is our flagship module that will let you do all sorts of GPU-powered visualization stuff. And Luma.gl is our lower level WebGL-2 framework that support all the deck.gl work that we are doing. We have a suite of applications internally and externally. A lot of them are open source or about to be open sourced. We have Kepler-GL. That's probably the most well-known if you are into geospatial visualization. It gives you a very nice UI to import data and just dynamically change how that data should be visualized using a very friendly UI. and will let you do the animation and filtering and stuff. We have an internal application for ATG, our self-driving car group, to visualize the logs that cars collect when they're traveling in the streets, and when they return, the ops and engineers will use this tool in the browser to inspect how the car performed. If anything went wrong, they will triage the issue and send it to the team that could best respond to it. This screenshot is showing us rendering bitmap layer, GeoJSON layer, point cloud layer, mesh layer, a total of, on average, anywhere between 50 to 100 layers in a log, and updating. This is playing at 10 frames per second, but the render rate is around 30 to 40 in a regular box and browser. It is a lot nicer than the old tooling that they had prior to the web age, where they had a Linux desktop-only software that can only run in a particular office on a particular configuration of hardware. We have something called Nebula GL that is built by our maps team to do map editing. So it's built on top of deck.gl and allow you to interact with all the geometries that's being rendered in a layer. This is a screencast from an internal tool that's used for fraud detection by our internal teams. It builds a graph that shows the relationship between user accounts, credit cards, phones, and etc. And they can identify patterns and dangerous behaviors just based on the networks between all these entities. And on a framework that we built on top of this has been in the works and is about to be open source, called GraphGL. It basically is based on deck.gl and lets you deal with InfoVis types of visualizations and render very large graphs in a very performant way. We also have internal tools that utilize deck.gl to show information for machine learning engineers to debug their algorithms and look into the layers they build, the models, and see what performed well and what went wrong. This kind of thing will be very expensive to draw using traditional ways, such as using D3 and SVG elements, is because the amount of data elements that's in each small plot. You can find a lot more learning resources for deck.gl on our website. We also have a site called Viz Academy that provides step-by-step tutorials to build certain applications. The whole team is here today, and we are we spend a lot of time on GitHub interacting with external users and answering their questions, and learn about their use cases and see how we can improve our library and API to support broader visualization needs by the community.